So now we're going to take a look at a worked example. And this is going to be a little bit more complicated in the simple formulation that I did in the theory part of the lecture. I wanted to add some things to it and just kind of show you if I add like load resistance, or not sure I shouldn't say load resistance, but fault resistance, and also substation resistance, how that's going to change the nature of the solution. And as I mentioned in the theory part, the example is that we have a substation that's converting 69 to 12.47 kV, and it has an impedance of 10%. And so in this particular case, we'll start off by assuming that there's no resistance to worry about. We have a base power of 25 MVA. That would be the rating of the substation in this case. We're going to use that to actually convert the per unit value into ohms. We have a straight capacitance. This would be due to the bus, any other devices that are connected up on the source side of that breaker. And let's assume that value is going to be 10,000 picofarads. Now, to make this problem a little bit more interesting, what we have is we've got a situation where we're going to have some fault resistance. And this would represent a real life type of a situation where, if we have like a tree branch or whatever, it wouldn't actually go to necessarily to a 0 ohm. Sometimes this is something we would refer to as like a high impedance type of fault. And so a lot of times what you'll see engineers do when they do short circuit analysis, they'll do the analysis like at 0 ohms, and they'll raise that fault resistance up to see if their solutions for protection still work. But we'll assume in this case that the circuit breaker clears the fault at a current 0. So what we want to do is we want to find the form for the transient recovery voltage so we can determine the peak stress on that circuit breaker. So the first thing we do is we've got to do some calculations. We need to go and we need to calculate what the base impedance is going to be. We're going to use this for converting that 0.1 per unit into ohms. I divide by 377 in order to convert this into inductance, and I get an inductance of 1.65 millihenries. What I am doing next in this case is I'm calculating a fault current. Now, why am I calculating the fault current in this case where I didn't do that before? Before, where I didn't have any fault resistance, I knew that when the current went through a 0, that the voltage source was going to be at its peak value, because we had a 90 degrees, an ideal 90-degree relationship. If I put a little bit of fault resistance in here now I'm changing that relationship. So when I hit a current 0, that source voltage is no longer at a peak value. So I need to do this calculation to figure out what is the source voltage when I hit the current 0. So what I'm doing is I'm calculating the steady state fault current. I'm assuming that we're in steady state when the breaker is going to be clearing the fault. And this is just going to be a simple RL circuit, but in this case, the resistance is going to be the resistance of the fault, that 0.5 ohms. So if I substitute in for the line to neutral value for the source voltage, note this time what I'm doing is I'm adding a point on wave value for theta. I'm putting that back in now. Now when I do the calculation for the current, I have an RMS magnitude of 9.02 kiloamperes, and note I have a phase shift of minus 51.2 degrees. It's nowhere near the minus 9 degrees I would expect if I just simply have an pure inductive circuit. So now the form of the source voltage is going to be the line value divided by the square root of 3 to get that to line to neutral, times the square root of 2. Let me just interrupt this for a second so I can get this back. Okay, so multiply that by the square root of 2 to get that to a 0 to peak value. And so now what I'm going to have, if I multiply that by cosine 377t plus theta, I have kind of a general expression for the source voltage that I could use Or what I need to figure out in this case is what theta is going to be for time equals 0. So now when I write out the relationship for the fault current in the time domain, then I take that phasor value and I basically convert that to the time domain by multiplying this RMS magnitude by square root of 2. Then this is going to be cosine 377t. I still have the point and wave angle in here, but then what I do is I take this minus 51.2 degrees and I put that into the expression for the cosine. Now, if I'm assuming that I have fault clearing occurring at a 0 crossing, then for time equals 0, I need to figure out, well, what is theta that gives me 0 for time equals 0? And so what this means is this expression in parentheses here for the cosine, this 377t plus theta minus 51.2, that's going to have to either be pi over 2 or 3 pi over 2. It turns out for the solution we're going to be looking for is we're going to set this to pi over 2. And so if I make this substitution in this particular case, what we're going to see at time equals 0, that theta is equal to pi over 2 plus 51.2 degrees. And if I make that substitution then into the expression for this voltage, what I'm going to see is that voltage, when I have a 0 crossing of the current, is now going to be minus 7,940 or minus 7.94 kilovolts, right? So it's not going to be the peak voltage anymore. It's actually going to be a lesser value, and I had to do this because the fact I was modeling a fault resistance, it changed the relationship between the source voltage and the fault current. So now, in order to solve the differential equation, what I'm going to do is I'm going to go ahead and assume that we have a natural frequency, a transient frequency that's going to be a lot higher than 377 radians per second. So when I set up the equivalent circuit for solving the differential equation, instead of having minus that peak voltage, now what I'm going to have is I'm going to have minus 7,940. I put the value of inductance in here. I have the value of capacitance in here. The fault resistance doesn't show up in the circuit anymore because the circuit breaker is open. So now that's out of the picture. And so when I go and look at my boundary conditions that I'm going to be using for solving, I'm going to have the fact that the current through the inductor is 0. The voltage across that capacitor is going to be 0. And the reason being is that even though it was in parallel with that fault resistance, when we hit the current 0, the voltage across that fault resistance was 0 as well. So we still have a situation where that capacitor voltage at time 0 is equal to 0. I can write a Kirchhoff voltage law relationship. So I have LD IDT plus the capacitor voltage is equal to the source voltage. This is simply a DC value. I'm going to have a current going through that capacitor that's going to be equal to C dV dt. And the current going through the inductor and the current going through the capacitor are going to be the same. So since this is a series circuit, I could substitute in for current in my Kirchhoff voltage law equation. All right, so I get this expression in parentheses. I can go through and I can divide by both sides of the equality by LC, and then this gives me the second derivative of voltage plus 1 over LC times voltage is equal to 1 over LC times Vs in this case, where Vs is the minus 7,940. So what do we have in steady state? Across that capacitor in steady state, remember the capacitor in a DC circuit is going to tend to look like an open circuit. That inductor is going to look like a short circuit. So basically in steady state, that capacitor is going to have that source voltage across it. And so what we would say in this case is VCSS in steady state is going to be whatever the source voltage is in our model. We solve the homogeneous equation to get the transit portion. So basically, instead of having a forcing function, we set this differential equation equal to 0. And the roots are going to correspond to solving the characteristic equation of s squared plus 1 over LC equals 0. So you have S1 and S2, the roots, plus and minus j times 1 over the square root of L times C. This 1 over the square root of LC is this natural frequency. This is the frequency of the transit. And we know that the form of the transit for this particular case is going to be something of the form of A1 cosine omega naught t plus A2 sine omega naught t. So when I put the two together, there's a constant part, there's a transit portion, and if I apply the boundary conditions, the capacitor voltage at time 0 is equal to 0, so that means that 0 is Vs plus A1, so that means that A1 is equal to minus Vs. And then the derivative of the voltage at time 0 is going to be the same as the current going through that inductor at time 0 divided by C, which turns out to be 0. So if I take the derivative of the voltage, set time equal to 0, then that enables me to solve for A2, and what we're going to see is we're going to see that A2 is equal to 0. So we get a solution that's kind of similar to what we had in the PowerPoint lecture. The resonant frequency, the frequency of the transit, that 1 over square root of LC, that's going to evaluate to 2.46 times 10 to the 5th radians per second, which is a little abstract. But if you convert this to kilohertz, then this converts to 40 kilohertz. So quite a bit higher than 62 hertz in this case. And then at the form of the voltage, this is going to be equal to minus 7,940 times the quantity of 1 minus a cosine of this resonant frequency times t for the time greater than 0 when the fault was cleared. So what's the peak stress on the circuit? Basically, that's going to occur when the cosine term's minus 1, when omega naught t is equal to pi. And in this case, if you just look at the magnitude is 15.2. So if you were going to compare that to what we would have had before, if we didn't have that fault resistance in there, traditionally we would have gotten 2 times the peak of the voltage source, right? That's if everything's kind of ideal. But what we have in this case is we have a lesser value for the transit recovery voltage peak because of the fact that we had some fault resistance in the circuit. Now, what would happen if we were going to consider the impact of having an X to R ratio for the source? Let's say the X to R ratio is equal to 6. And so what we need to do in this case is we need to figure out what R and X are going to be. And I'm going to go ahead and just assume that the magnitude of the impedance is still 0.1. And so again, we convert that to ohms, but this time this is going to equate to the square root of R squared plus X squared from the X to R ratio. We know that X is 6 times R. Substitute in, and we get an expression for calculating R sub S for the substation or the source, and then X is 6 times this value right here. And so now what we have for the fault current is a slightly different expression. Instead of just simply having the fault resistance, we're going to have a little bit of resistance associated with the source in this case. We're going to get a little bit less fault current, and we're going to get a different phase shift. And so again, I'm going to include my point on wave angle and the voltage. I'm going to calculate the fault current. I get a different angle. We look at where does a zero crossing occur. Well, that's going to correspond to a different value of theta. This time it's going to be theta is equal to pi over 2 plus 45.5 degrees. And then the source voltage at this time equals 0 then is going to be the minus 7.262 kV. So what this did is it shifted the fault current a little bit more So before, what we were getting is we were getting minus 7,940. Now in this case we're getting minus 7,262. So it changes again, changes by a little bit. But when I solve, again, when the circuit breaker opens, the fault resistance is out of the picture. But this time, now I've got resistance in the circuit due to the source resistances. Now I have an RLC circuit. And this time what I would expect to see in the solution, I would expect to see some damping. So kind of continuing on, if I write the differential equation, then I have the LDIT plus RI plus capacitor voltage is equal to this DC source voltage. Again, I make the substitution that current's equal to C dV dt, substitute in, divide both sides by LC, and this gives me the formula solution. And if you didn't believe me before that, that steady state capacitor voltage tended to the source voltage, I mean, if we just assumed it was going to be a constant value, which we would have in a DC circuit, I could just substitute in for that constant value in my differential equation, and we would see that indeed that this steady state value is just simply going to be the source voltage, which in this case is the minus 7,262. So we have a different characteristic equation. The characteristic equation is S squared plus R over L, S plus 1 over LC. We set this up for solving a quadratic in order to get the roots of the characteristic equation. So if B is R over L, C is 1 over LC, A is equal to 1, then I can find my roots by solving this quadratic equation. And this quadratic equation for the roots is going to have a real part, which is minus 31.4. So this is going to be associated with the exponential term that's going to decay with time. And then there's the oscillatory term, which is 2.48 times 10 to the fifth. So if we look to see what this gave us before, it does change the resonant frequency in the third place. It does change it a little bit, but it's only changing it by about 1% or so. So it doesn't really factor into changing that resonant frequency too much, but it causes a slight change. So now if we look at the transit portion of this, instead of just having A1 times a cosine term and A2 times a sine term, we have to put this exponential damping term in here, which means that as time increases, then we're going to have kind of an envelope that's going to decay out with time. So the total form of the solution before we get these constants A1 and A2 is shown right here in the box right here, right? So minus 7,262 plus e to the minus 31.4 t times its quantity in brackets. So now I have to apply the boundary conditions. This initial capacitor voltage is still 0. Again, if we clear it at a current 0, the voltage across that fault resistance is 0. So again, it keeps that initial capacitor voltage at 0. And so this gives us an equation for solving for A1. Now, what gets a little tougher now is getting A2, because now we've got two terms multiplied by each other. There's an exponential term, which is a function of time, and there's a cosine sinusoidal terms that are a function of time. So what we need to do now is we need to apply the chain rule. So what the chain rule says, if you have two functions that are both a function of time, let's say we want the derivative with a function of time, what you would do is you would take the derivative of the first term, f, multiply that by g, and then add to that f times the derivative of the g term with respect to time. So when we do this, we take that derivative of voltage with respect to time, we set time to 0. Again, that still corresponds to the initial inductor current divided by C, which was equal to 0 because we cleared at a 0 crossing still. And this is going to be equal to the derivative of this expression set at time equals 0. So what you do is you have to take the derivative of the exponential term first. This kicks out a minus 31.4. You have then the second term where you have e evaluated at time 0. Then you have to take the derivative of the sinusoidal terms. They're going to kick out a coefficient of omega. But the term we're interested in is the A2 term, where the sine, when you take the derivative, gives us omega times a cosine. And when we then process this, we can solve for A2, where A2 is 31.4 times A1 over omega 1. And we end up with this term of 0.9204 for A2. So when I put this together, we've got two terms. We've got the steady state portion, we've got the transit portion. You see this second term we're adding in here, due to the fact that we added that resistance into the circuit, it's not really that big. It changes a little bit. For the most part, it's kind of similar to what we had before. So if you ran into this sort of a situation, and if you were just going to use maybe like the previous solution we had for the case where we ignored that resistance, we'd get pretty similar answers in this case. But if you want to try to get it more accuracy, then you could go with this formulation that includes the source resistance in here. So again, we're looking at the situation where this is going to give us a worst case peak. And this is, if we ignore this second term, this is going to occur when this cosine term has an argument of pi. That makes the cosine minus. Basically, we get minus 7262 times 2, which is minus 14.52. And so when we do the PSCAD simulation, what we want to do is we want to see, to what degree this matches up. So it drops the peak voltage down just a little bit more. And the thing we got to be thinking about when we're doing these types of analysis is, well, what's good enough for the solution, right? I mean, if we can get within 5 or 10%, we're probably doing pretty good. And there's always going to be some other resistance, some other reactance that you can include in the formulation. But what you would do is you would basically work with, like a second order differential equation. You kind of choose the dominant R and the dominant L and the dominant C, and you kind of go with that, and you get close. And see, usually that's good enough given the uncertainty in the field parameters, as far as doing something by hand. And then if you want to do something more accurate, then you could use the computer simulation for that. So anyway, what I'll do next is I'll show you what this looks like in PSCAD. And then what you could do is you can actually compare the results and just make sure that your hand analysis was correct by looking at the results you got from PSCAD.